Günaydın arkadaşlar. Birazdan başlayacağız. Varsa bu arada sorunuz sorabilirsiniz. Okay, maybe let's start with a recall. Let us recall what we did last time. We defined Laplace transform last time. Here is the definition of the Laplace transform. You have a piecewise continuous function, and the Laplace transform of this function is defined by L of f of t is from 0 to infinity e to the minus st f of t dt, right? That was the definition of the Laplace transform. And we had some well-known formulas for simple functions like the following. L of 1 is equal to 1 over s. By the way, we will denote this by f, capital F of s. It's a function of s. Second, L of e to the at was 1 over s minus a. Third, maybe L of cosine at is s over s squared plus a squared. Similarly, L of sine at is now it's a over s squared plus a squared. Laplace transform of t to the n is n factorial over s to n plus 1. Here n is like 0, 1, 2, and so on. It's a natural number. These are common used formulas for Laplace transform, and we had some rules like this. If, let's say, L of f of t, let's say it is f of s, then let's say a here, you can multiply this f of t by e to the at, and the Laplace transform is basically shifting of the original Laplace transform like this, okay? B here, when you multiply your function by t, you differentiate the Laplace transform with respect to s and negative of this ds, sorry. And one more here, c, Laplace transform of f of some constant c times t is 1 over f, capital F, s over c. So these are some useful rules when we deal with Laplace transform, then we will use it a lot, okay? Then we define step functions, because when we solve the equations with Laplace transform, Laplace transform is especially useful when the right-hand side of the equation is a discontinuous function. maybe let me also remind this when we solve the differential equation, we use this, right? Maybe let's write this as a rule as well. When we apply Laplace transform to the nth derivative of f, it's basically s to the n. Yeah, okay, let's keep it like this. L of f of t. I can also say f of s, but anyway, let's keep it like this. Minus s to the n minus 1, f of 0, right? You continue like this, minus s to the n minus 2, f prime 0, and finally minus f to the n minus first derivative at 0, okay? This is also useful when we solve the equations, differential equations with Laplace transform. All right, let me remind the step function as well. We had this step functions. These are basically simple functions like this UCT here. It depends on C. It is 0 if T is less than C. It's 1 if T is greater than or equals C, okay? Step function, it's called step function because it looks like a step. It's this, right? When T is greater than or equal C, it's 1, otherwise it's 0, okay? 0 here. Color. All right, so this is UCT. And the nice thing is when you have piecewise discontinuous function, you can write in terms of the step functions. And we can compute the Laplace transform of step functions easily. So this will help to find the Laplace transform of a piecewise continuous function, okay? So what I'm saying is, if you remember, g of t is like this. It's given by some function h1t, if t is less than c1, h2t. Another function if t is between c2 and c1, and you continue like this, okay? Then you can write g of t as h1t plus u c1t times h2 minus h1 okay, plus u, now you continue with c2, u c2 t, and multiply with now next one, it's h3 minus h2. And it goes like that, okay? It goes like that. And we also had this, remember, the Laplace transform of the step function, UCT, is e to the minus cs over s, where c is positive and the real part of s is positive. S can be a complex number. In that case, we assume that real part of s is positive in order to have a convergent Laplace transform. Okay, remember, Laplace transform is an improper integral. And in order this improper integral be convergent, we need some conditions on s. Here, for instance, real part of s must be positive. Okay. Any question so far? Var mı buraya kadar soru arkadaşlar? Okay, let's do some examples now. Or maybe before the example, let's, so this is new lecture now. Let's also talk about this important fact, which says L of UCT times f of t minus c, okay? It's like backward shift. It's equal to e to the minus sc times L of f of t. Again, here real part of s is positive, c is positive, and so on, but we don't write every time. Okay, we have this. This is also useful when we do some computations. You will see later. Let's put this in box. Well, the proof is not very difficult. Maybe let's prove it. Why this is true. Well, what is L of UCF? It's L of here UCT f t minus c, right? We will compute this. It's basically improper integral from 0 to infinity UCT f t minus c e to the minus st dt. This is the definition of the Laplace transform. We can simplify this because remember here, this function UCT, this one, it is 0 if t is smaller than c. So this tells you basically you can start from c instead of 0 because before c it is 0, right? Everything will be 0. And after c it is 1, so this is going to be f t minus c e to the minus st, okay? So it becomes simpler after you do this. Well, now we change the variable. So let's say here, we change the variable like this. Let's say this is tau, here another variable introduced here, t minus c. So this integral becomes what? The integral becomes basically integral from, now we will write everything in terms of tau. This is tau. When t is equal to c, tau will be 0. And this is to infinity, okay? F of tau here, e to the minus s times small t here will be tau plus c. D tau and dt are the same. So this is basically e to the minus, so you multiply this 2, s and c, it's a constant with respect to tau, so it's going to be e to the minus s times c, and integral here from 0 to infinity f of tau here e to the minus s tau d tau. The nice thing is this integral is nothing but Laplace transform of f. Okay, so this is simply the Laplace transform of f. And we are done, right? So this proves that this formula here, which will be used later when we work with discontinuous functions. Let's do one example now to understand this formula better. Let's say we have G1 here, or GT, sorry, is U sub 1 T plus T minus 3 U sub 3 T, okay? And what is the Laplace transform of this? Well, the Laplace transform of G of T is the Laplace transform of U1 plus the Laplace transform of T minus 3 times U sub 3T. Okay. Well, the first one is easy. We use this formula here, e to the minus cs over s, right? So this part is nothing but e to the minus, here this is c. C is 1, minus c minus 1 times s over, what was it, s, right? Let's go back to the formula, it is s here, okay? So you divide this by s. Okay, so this is the easy part. We just apply the formula directly. Now we have a here shift t minus 3. So what you can do is you can think of this like in the box here. UCT ft minus c. What is f in this example? What is f of t here?
Just T.
Can you guess?
Just T.
Good. It is just t because when you say from here f of t is equal to t, then ft minus 3 is equal to f of t minus 3 will be equal to t minus 3, and you will get this, right? So this tells you basically it is equal to plus e to the minus cs, which is minus sc minus or cs minus 3s times L of f of t, L of t. Okay, f of t is L of t. So we use this formula here. This one. Well, we know what L of t is, right? L of t is basically. You use this formula, remember again here, this one. When n is equal to 1, it's 1 over s square. Okay, so this is 1 over s squared. So maybe let's write this explicit. Okay, any question with this example? Var mı soru? Okay, let's do more examples with differential equations, and right-hand side is continuous. So this is basically chapter 6.4 in the book, differential equations. With discontinuous right-hand side, so let's do this example. Solve the initial value problem. Is equal to UTT minus U3T. So right-hand side is discontinuous. It's given in terms of step functions, right? Difference of two step functions. And initial values are y0 is equal to y prime 0 derivative is equal to 0, okay? So at the initial point 0, the function and the derivative is 0. Well, we apply the Laplace transform, right? So solution here. Well, for this problem, it doesn't say how to solve it. But since the right-hand side is discontinuous, there is not much rule here. We cannot apply the others, like, you know, this variation of parameters or other things, because right-hand side is discontinuous and it's hard to apply other methods. With Laplace transform, it's going to be easier, okay? So let us apply Laplace transform. L of y double prime plus 3y prime plus 2y will be the Laplace transform of UTT minus U3T, U2 minus U3. Okay, well, let's expand left-hand side. It's going to be s squared y of s, right? Minus it's s times y 0, right? Minus y, let's write this. Minus y prime 0. Okay, this is for here, y double prime. Now we move to the y prime, this one. That's okay. So it's going to be plus 3 times s times ys, okay, minus y 0. Okay. Well, finally, 2 times this one here, 2 times ys. This is equal to right-hand side. On the right-hand side, we have step functions, and remember the formula for the step function, e to the minus 2s over s. Okay, this is the first one. The second one, minus e to the minus 3s over s. Well, the nice thing is these are 0. So these are given here, y0 and y prime 0, they are 0. So we get rid of this and this one. And from this, let's take this in ys parentheses on the left-hand side. It's s squared plus 3s plus 2. On the right-hand side, we have e to the minus 2s over s minus e to the minus 3s over s. Now what I will do is, I will try to do partial fraction after some work. So ys, maybe let's write it like this first. E to the minus 2s over s squared plus 3s plus 2 times s. This is one thing, minus e to the minus 3s over s squared plus 3s plus 2 times s. Well, we can split the bottom here. The bottom is basically s plus 2 times s plus 1, right? So maybe let's do this on a side. Partial fraction. I will not do it long, but let's keep it this side. 1 over here, s squared, or maybe let's write it like this, s plus 2 times s plus 1 times s is it's 2, right? 2. Yeah. Okay, so you can do the partial fraction and you will get, I will not do it here, but you can check yourself. It's plus minus 1 over s plus 1 plus 1/2 over s plus 2. You can find this numbers 1/2 and minus 1, doing applying here partial fraction. Okay, maybe let's just here partial fraction. You basically equalize the denominators and find the coefficients of s plus 1 and s plus 2. Well, now this tells you basically, remember we will apply the inverse Laplace transform to find y of t, but we also have this term here, right? So we will use one of the rules later, but let's first find the inverse transform of inverse transform of 1 over s plus 2 times s plus 1 times s. It's from this here, the inverse transform of, forget this, 1/2 times inverse transform of 1 over s minus inverse transform of 1 over s plus 1 plus 1 over 2 times inverse transform of 1 over s plus 2. Well, what is the inverse transform of 1 over s? That means for which function we have 1 over s as a Laplace transform? It's 1, right? So this is 1 over 2, basically. Next one, 1 over s plus 1, it's e to the minus s, right? Okay. Minus t, sorry, minus t. Next one, 1 over 2 e to the minus 2t. Do you have any questions so far? But we need the inverse transform of e to the minus 2s over this, okay? So we will use this to get the inverse transform of this here, e to the minus 2s over s squared plus blah, blah, okay? So maybe let's say this is here, call it f of t, give a name f of t for this, then we need this, right? Inverse transform of e to the minus 2s over s times s squared. Or maybe let's write like this, s times s plus 2 times s plus 1. This one. Well, it's going to be what? It's going to be, remember the formula here, this one here, okay? It says simply that when you apply Laplace transform to UCF, you will get something like this. So here, we have this one, okay? So this is nothing but LU2 times f of t minus 2, right? Right, because that means basically when you apply here on the right hand side, when you apply the Laplace transform to this side, you will get e to the minus 2s over blah blah f of t, Laplace transform of f of t, which is s 1 over s times s plus 2 times s plus 1. So we get that, right? We're almost done here. So this tells you basically it's equal to, let's write it now, u2t times f of t minus 2 is, this here is f of t, okay? So you replace t by t minus 2, so you will get simply 1 over 2 minus e to the minus t minus 2 plus 1 over 2 e to the minus 2 times t minus 2. All right, so this is one of the inverse Laplace on the right-hand side. Now we will deal with this one in a similar way. It's not much different. You simply replace minus 2 by minus 3, okay? So you will get the following, basically. Similarly, the inverse Laplace of e to the minus 3s over s times s plus 2 times s plus 1 is basically u 3t, okay, times f of t minus 3, which is this one, u3t times the same f we use here, 1 over 2 minus e to the minus t minus 3 plus 1 over 2 times e to the minus 2 t minus 3. Okay, this one. Now, remember here, y of s is equal to right-hand side. So we apply the inverse Laplace to find y of t. So from, maybe let's put here star. Okay. So by star, we get that y of t is equal to the first one here, this. This one plus this one. From this, let's copy this again. Anyway, let's write it. So it's going to be plus, okay, there's something wrong with this. Plus u3t 1 over 2 minus e to the minus t minus 3 plus 1 over 2 e to the minus 2 t minus 3. Okay. All right. Any question with this example? Var mı soru arkadaşlar bu soruyla ilgili?
Hocam ben bir şey sorabilir miyim? Yani öyle çok
Sanırım
soru
eksi
gibi,
olacak. Tabii.
çok soru
Şurada
gibi
eksi
değil de
olsun.
biraz
Tamam.
böyle şey uygulamayla ilgili.
Eksi
Şimdi
olsun.
yani Laplace, işte Laplace'ın tersi diyelim. E üzeri eksi 2s bölü s çarpı s artı 2. Hani o u subprime t çarpı f fonksiyonu t eksi 2 ya.
Evet.
Yani
şu demek. Şöyle söyleyeyim. Mesela şuna bakalım. Şu kısım aslında şu demek. L of u2t times f of t minus 2 eşittir e to the minus 2s times L of f of t. Değil mi?
Evet, evet.
Çünkü bir de
Tamam, f of t'nin Laplace'ı da
f of t'nin Laplace'ı buydu, evet, şu kısım.
biraz daha iyi oldu sanırım hocam. Biraz daha bakayım ben tek başıma. Tamam hocam, teşekkürler.
Peki, başka soru? Any other question? All right, let's continue. Let's do another example. Open a new page. Solve the initial value problem. Y double prime plus 4y is equal to f of t, y0 and y prime 0 are 0, where here f of t is a piecewise different function if t is less than 3, it's 3t minus 9 if t is between 3 and 6. (15 minus t if t is between 6 and 15, and 0 if t is greater than or equal 15. Okay? Okay, we will solve this equation. Well, again, the right-hand side is discontinuous. First, we will write right-hand side in terms of the step functions, and then apply Laplace transform. Let's do it. Solution here. So we can write f of t as the following. We start with h1. h1 is, so this is h1. This is h2. Here is h3, and so on. Okay, h4. So you remember, you start with h1, it is 0 plus, next, you multiply, C1 is 3. So this is C1, this is C2, this is C3. Okay, we have this. So use C1, which is 3t times h2 minus h1, which is 3t minus 9, plus next one is u sub c2, which is 6, times, now we have h3 minus h2, So we will write like this. H3 is 15 minus t minus 3t minus 9. Okay. Next, plus C3 is 15. So U sub 15 times, well, again, it's 0, H4 is 0, 0 minus H3, 15 minus T. That's it. So this is your f of t, okay? This is very important to write like this because we will apply Laplace transform now, and we know how to compute the Laplace transform for the step function. Well, let's maybe write like this. Here, f of t is u sub 3t. You can write 3t minus 9 as 3 times t minus 3. This is easier to work because we have 3 here and 3 here. And remember, when you have like this, you can easily compute the Laplace transform. We had a rule, okay, for this sort of function. Plus u sub 6, this one here, 15 minus t minus 3t minus 4t plus 24, right? So this is minus 4t plus 24. And again, we have here 6. So it's like, if you can write this like t minus 6 times something, that's going to be easier to work. So that's why I will write this as minus 4 times t minus 6. Or maybe let's write like this. T minus 6 times minus 4. Okay, that's one. And here, this one, it is t minus 15. This is already in the good form because we have 15 here, okay? So we have u sub 15 t times t minus 15, okay? All right, so we modify f of t, we rewrite it basically, and it's in the good form now. Well, next we apply the Laplace transform. Let's apply the Laplace transform here to start. So we get what? We get is the following. The Laplace transform of y double prime plus 4y is equal to the Laplace transform of f of t. Okay. Well, this side is easy. This side is nothing but s squared times ys minus s times y0, but y0 is 0, y prime 0 is 0, so you will get nothing from that part, plus 4 times ys, right? So I don't write the remainder part here, y0 and y prime 0, because they are both 0. On the right-hand side, we have this. ut, here we use this one, okay? ut3. What is the Laplace transform of ut3? It is, remember, Well, you can think of this like here. Okay, maybe let's write it like this first. It's 3 times the Laplace transform of t minus 3 times u 3t, okay? Plus minus 4 times the Laplace transform of u6t t minus 6, okay? Plus Laplace transform of u15 t times t minus 15, okay? Well, remember the formula here. When you have the Laplace transform of this one, right? So we use this formula here. We will use it here. L of UCT f of t minus c is equal to e to the minus sc times L of f of t. We will use this, okay? This formula. What is in the first part? What is f? F of t is t, right? So the first one here, this one, f of t is t because we have t minus 3 is, f of t minus 3 is t minus 3 then. So it's 3 times e to the, what is c here? C is 3 minus 3c L of t, okay, L of t. The next one, minus 4 times, well, again, here, f of t is t again, but c is now 6. So e to the minus 6s times L of t again. Okay. Finally, we have similar e to the minus 15 s times L of t again. L of t is 1 over s square. So we get this 3 times e to the minus 3s over s square minus 4 times e to the minus 6s over s square plus e to the minus 15s over s square. Okay. Well, on the right-hand side here, we had this one. And this is nothing but ys parentheses s squared plus 4. So you divide everything by s squared plus 4 and you will get the following. Ys is 3 e to the minus 3s over s squared times s squared plus 4 minus 4 times e to the minus 6s over s squared times s squared plus 4 plus e to the minus 15s over s squared times s squared plus 4. Okay. Now we will apply the inverse Laplace transform. To do that, we need partial fraction. So what I would do is, first, let's deal with 1 over s squared times s squared plus 4. Well, maybe let's do this on a side. Again, you can check this yourself, this partial fraction. 1 over s squared times s squared plus 4. Maybe let's write a little bit more here. 1 over s squared times s squared plus 4. How do you expand this in the partial fraction? It's going to be, since we have double root for 0, we will write like this: a over s plus b over s squared. S squared plus 4 is irreducible factor, so you cannot split. And you read the 1 degree less polynomial on the top, cs plus d over s squared plus 4. And you find a, b, c, d here by equalizing the denominators. Now this part is simple. From here, a will be 0. B will be 1 over 4. C will be 0. Okay. And D is minus 1 over 4. You can check this yourself, which tells you basically, the following: the inverse Laplace of 1 over s squared times s squared plus 4 is nothing but, okay, a is 0, we get nothing. B is 1 over 4, so you will get 1 over 4 times the inverse Laplace of 1 over s squared. C is 0, we get nothing again. D is minus 1 over 4, minus 1 over 4 times the inverse Laplace of 1 over s squared plus 4. Okay, let's write this down here. The first one here, what is the inverse transform of 1 over s squared? It's basically t, right? So t over 4. The next one here, we have 1 over 4 minus 1 over 4 times the inverse Laplace of 1 over s squared plus 4. This is like sine, right? Sine function. But sine 2t will give you here 2. So you have 1 here. That's why we need to divide this by 2 sine 2t, okay? This follows from here. Or maybe let's simplify this. It's t over 4 minus 1 over 8 sine 2t. But remember here, we need a simple modification here. We multiply this with e to the minus 3s, okay? And here we have this inverse transform of that. Well, so what I will do is, if I say this is, let's give a name for this. Let's call it age of t, okay? This is age of t. So y of t will be what? It's 3 times the inverse transform of this, okay. 3 times L inverse, what was it? E to the minus 3s over s square times s square plus 4. Next, minus 4 times inverse transform of, what was it? E to the minus 6s over s square. Okay. Next, it's minus 15s over s square. Minus 15s over s square. Okay, well, s squared times, sorry, s squared times s squared plus 4 everywhere here and here. It's like this, plus 4, s squared plus 4, and so this and this. And above here, we find all this inverse without e to the minus 3s. Now we use again the same formula here, this one. Okay? Which tells you basically the inverse transform of this here, e to the minus 3s, e to the minus, what does it say here again? Right, so it says basically the inverse Laplace transform of this one here is equal to uct times f of t minus s, t minus c, okay? So this is gonna be equal to, in the first one, c is equal to 3, so 3 times u 3t times, what is f here, h here, h is about this one, okay? So this is h t minus 3, okay? This. And next, similar, minus 4 times, again, now c is 6, u 6t times h t minus 6. And finally, this is u 15t times h t minus 15. Okay, that's it. And here age is given above, so you can write this explicit. Maybe let's skip that part because you simply write here where, maybe let's write it like this, where age of t is t over 4 minus sine 2t over 8. Okay, it's enough to write like this. So this is y of t, okay, small y, of course. Y of t like this. Okay, any question with this example? Var mı soru arkadaşlar bununla ilgili? Oh, we over the time. Let's give a break here for 10 minutes. So let's meet at, okay, let's meet at 10. All right, welcome back. Var mı soru arkadaşlar? Devam etmeden önce. Okay, let's now talk about another important function, impulse function. This is 6.5 in the book.
Hocam ben ufacık bir şey sorabilir miyim? Burada mesela t-3 falan fonksiyon olarak yerine yazmamıza gerek yok değil mi? Açık açık. Öyle de t-6 falan bıraksak olur yani. Bu kadar yazmamız
Benim
yeterli.
yazdığım gibi bıraksanız yeterli.
Tamam hocam, teşekkürler.
All right, impulse function. So what is the goal here? Maybe let's write this first. The goal here is to solve an equation like this. Is equal to G let's say it's a function, depends on some epsilon, small, okay? Here where G of epsilon, G sub epsilon, T is large, very large, during a short time interval. Interval T between some T0 minus epsilon, T0 plus epsilon, and otherwise G sub epsilon T is 0, okay? So basically in a short interval, time interval, G will be very large, right-hand side of the equation will be very large, and outside of this small interval, short interval time, the function will be 0, okay? And for simplicity, we will take T0 is equal to 0. Take T sub 0 is equal to 0 for simplicity, okay? So basically what I'm saying is like the function looks like the following. We have an interval like this, minus epsilon, okay? And in this small interval from minus epsilon to epsilon, G will be very large. For instance, you can take here, it's 1 over epsilon. 1 over epsilon is large when epsilon is small, right? Okay, and otherwise it is 0. So it's like this. It's 0 here and here. Well, you can easily see that the integral of G epsilon t from minus epsilon to epsilon, it's basically the area under this line here. It is the rectangle, right? Area of the rectangle, this rectangle, which is basically 2, right? Maybe let's normalize it and make it 1. Okay, let's take 1 over 2 epsilon here instead of 1 over epsilon. So this is 1 over 2 epsilon. Now, it satisfies a similar condition. Now, in the interval, 1 over 2 epsilon is very large, okay? But now the integral is equal to 1. Okay. So let's see what happens when epsilon goes to 0. As epsilon goes to 0, these functions will be like, maybe let's draw this here. You will have functions like this. From minus epsilon to epsilon. First you start epsilon like that. And 1 over 2 epsilon is somewhere here. I know this is not a very good picture, but it will give the idea at least. It's like this, okay? And as epsilon gets smaller, you will get something like this. For instance, if epsilon is small, you will get this one and that one. And 1 over 2 epsilon will be somewhere here. Okay, and this. And if it is even smaller, you will get, for instance, something like this. Okay. So you see here, as epsilon gets smaller, the value of the function will be very large, but the area will be same. Area is always 1. So the integral of this function will be always 1. So this is g sub epsilon, with new epsilon. Even with smaller epsilon, we have this. The integral will be same, but the value of the function will be large. In a shorter interval, okay? Well, in the limit, you will get something like, maybe let's take it on the side here. So as epsilon goes to 0, you will get something like this. It's like it's like something like that. So it's going up very sharp, like this, right? So this is what it looks like as epsilon goes to 0. We have kind of a limit of these functions. Well, we define the impulse function with this limit. Okay, so we define impulse function delta. This will be denoted by delta t, okay, delta t by. So delta t is simply the limit of g epsilon t as epsilon goes to 0. Okay. Well, this definition is fine, but it's hard to understand what it looks like. Because as epsilon goes to 0, what happens? Well, it's like the function becomes 0 except for t is equal to 0, kind of. Okay, so, well, maybe we can define this in another way. Formally, delta t is defined by the following. So here is the formal definition of the impulse function, which is more useful than this limit definition, because limit definition doesn't allow you to do some computations all the time. Well, first of all, the impulse function delta t is the function. Well, I will put this in here quotation because it's not really a function. Okay, delta t is not really a function. You will see from the properties now, but it's called a distribution, not really a function. Not really a function, but a distribution. Well, you don't need to know what this is, okay? If you are curious about this, you can Google it. But in this course, we will not talk about distributions more than this, okay? It's another story, but for general culture, it's good to know it's a distribution, not a function, satisfying the followings. So it's a distribution satisfying the following properties. The first one is delta t is 0 if t is different from 0. So this you can see from the picture as well, right? As epsilon goes to 0, that means you will exclude any number except for 0. And outside of the interval, functions are 0. So in the limit, delta t will be 0 if t is different from 0. And the second property is the integral from -infinity to infinity of delta t dt. The integral will be 1, right? This is what you see from the picture as well. The integral of g epsilon is always 1, so the limit will be 1 as well. The limit of the integrals will be 1 as well. So with these two properties, we define a distribution. It's like a function, but there is no function which satisfies these two equations, so two properties, so it's not a function, okay? Anyway, so let's compute the Laplace transform of this impulse function. So we say here function, but as I said, it's like pseudo function, okay? It's not really a function. So let's compute the Laplace transform of delta t, the impulse function. Well, to compute this, we use this the first definition of impulse function with respect to this limit, okay? With respect to this limit definition. So what it says basically, impulse function is the limit of g epsilon t as epsilon goes to 0. So we will compute first Laplace transform of g epsilon t. And this is easy to compute because it's nothing but 0 to infinity g epsilon times e to the minus st dt. Well, g epsilon is 0 if t is bigger than epsilon. So this is nothing but 0 to epsilon. Otherwise, it's 1 over 2 epsilon, right? And well, here we have to be careful with the definition. Let's put here 1 epsilon. So we use this definition when, so we use here sort of like t is always positive. In that case, we use this definition of impulse function. It's 1 over epsilon from epsilon, 0 to epsilon, okay? So we shift the impulse function to the right with this now, okay? Again, the integral will be 1 always. So this is g epsilon, okay? G epsilon t. All right, so it's basically 1 over epsilon times e to the minus st dt. Well, this is, you can compute easily. 1 over epsilon is out, e to the minus st over minus s. T is from 0 to epsilon. So we get simply minus 1 over epsilon s e to the minus epsilon s minus 1. Now, as epsilon goes to 0, we will get epsilon goes to 0, we will get 1 over well, it's not clear what it is because it's 0 over 0, right? So we use L'Hopital here. Using L'Hopital, you can easily show that this is 1. Okay, here we use, you can check this yourself, use L'Hopital to find this limit. Okay, so we see that the Laplace transform of g epsilon is 1. So this implies basically the Laplace transform of impulse function. Impulse function is the limit of g epsilon, so it's equal to 1 as well. Okay, so this is what we get at the end. And in a similar way, you can show the following. Similarly, Laplace transform of delta t minus t0. So you shift your delta. It's e to the minus s t0. Okay. This. All right, let's do an example with impulse function. Any question so far? Var mı soru buraya kadar arkadaşlar?
Hocam, bilir miyim? Şimdi biz
Evet.
böyle g of epsilon böyle tanımladık.
Evet.
İşte böyle de diferansiyel denklemin sağ tarafında kalan. Hı-hı. Sonra onun limitine impulse function dedik.
Evet, doğru.
bunu tanımlarken de şey kullandık. Çok küçük aralıkta çok büyük olduğu için 1 bölü olarak ifade ettik ve integrali hep 1 oluyor dedik.
Evet, doğru.
Tamam.
Evet, aynen öyle. Yani bu şey gibi işte böyle fonksiyon öyle bir olacak işte bir anda çok büyük mesela elektrik veriyorsun.
Çarpışmalar gibi ya da hani
Evet ya da çarpışma gibi aynen ya da işte elektrik akımı bir anda geliyor, yükseliyor sonra düşüyor falan. Hani o tip denklemleri çözmek için daha çok bu işte elektronikçilerin uğraştığı problemlerle ilgili biraz.
bir de böyle bizim konumuzla çok alakalı değil ama distribution kısmını tam şey yapamadım. Neden fonksiyon değil? Çünkü şu iki şeyi satisfy etmediği için.
Evet, bu şu iki koşulu sağlayan bir fonksiyon olamaz. Yani çünkü bir fonksiyon eğer sadece bir noktada e, sıfır değil ve diğer noktalarda sıfırsa bu onu söylüyor. Diyor ki bu fonksiyon sadece t noktasında yaşıyor, sıfır noktasında yaşıyor. Onun dışında ölüyor. Böyle bir fonksiyon olabilir, tamam. Ama bu fonksiyon integrali o zaman bir olamaz.
Hmm.
Yani şöyle bir fonksiyon aldın diyelim. Sadece şurada bir şeye eşit. Bilmiyoruz ne olduğunu ama geri tarafta sıfır. Şurada sıfır. Bu fonksiyon integrali sıfır olur normalde. Eğer fonksiyon olursa. Dolayısıyla böyle bir fonksiyon olamaz. Bu
Tamam.
bir fonksiyon değil. Bu tip şeylere biz böyle yarı fonksiyon gibi şeyler diyoruz. İşte ona da genel ismi distribution.
Tamam. Tamam hocam.
Tamam.
Teşekkürler.
Hı hı. Distribution ayrı bir teorisi var. O yüzden onlara hiç girmiyoruz. Sadece bunu bilseniz şu an yeterli sizin için. Peki, alright. So what's important here, we know the Laplace transform of the impulse function is 1, and when you shift it, it's e to the minus st0. You can obtain this second one from the first one easily. I will not do it, but maybe let me give this as an exercise. Obtain this yourself with the definition of Laplace transform. This is an exercise for, okay? Okay, well, let's do one example, then we will stop. So let's solve this equation. 2y double prime plus y prime plus 2y is equal to the impulse function t minus 5. When you say impulse function t minus 5, you shift the impulse function by 5 units. So that means if t is not equal to 5, right-hand side is 0. If t is equal to 5, right-hand side is not 0, okay? So basically, this is like at 5, the function takes very large values like this, okay? And then it dies, okay? Like that. Okay, good. Well, let's solve this with initial values. Y0 is equal to y prime 0 is equal to 0. Solution. We apply the Laplace transform to the both sides. L of 2 times y prime double prime plus y prime plus 2y is equal to L of t minus 5. Okay. Well, on the left-hand side, we have 2 times s squared times ys. I will not write the remainders because y0 and y prime 0 are 0, so they will vanish. Plus s times ys plus 2 times ys. On the right-hand side, we have the Laplace transform of the impulse function at 5. So it is minus e to the minus t0s. T0 is 5. E to the minus 5s, right? Okay. Well, this tells you basically, if you take this here in ys parentheses, this will be 2s squared plus s plus 2. Okay. So from here, ys will be e to the minus 5s over, okay, 2s squared plus s plus 2. Now we will apply the inverse Laplace transform to get the solution. To do that, what we can do is, well, the thing is we cannot split this. This is irreducible, okay? Here, this is irreducible. You can check with the discriminant. Discriminant is negative, okay? So you cannot factor out. You can check the discriminant, which is negative. But what we can do is we can write this like, we can complete this to a square. So it's like, you take 2 out, it's s squared plus s over 2 plus 1, or you can write s plus 1 over 4 squared. Now s squared plus s over 2 plus 1 over 16, but you need 1. So it's going to be 15 over 16. Add this and make it 1. They are the same, right? But now it looks like a sine function, Laplace of sine function. So what is the inverse Laplace of 1 over s plus 1 over 4 square plus 15 over 16, okay? Well, without this, it will be like sine of here, at. So this is the square of root 15 over 4, right? So it's like sine of okay. Or maybe let's do this without this first. Okay, s squared. First, let's do this. It's sine over sine root 15 over 4t over this one, because you need this on the top, so we have 1 here only. So it's going to be 4 over root 15. But we need s plus 1 squared, so you shift basically, and this tells you that the inverse 1 over s plus 4 squared plus 15 over 16, it's the shifting of the Laplace transform. So it's going to be 4 over root 15, shift by 4. So it's going to be e to the minus t over 4. Okay. Sine root 15 over 4t, right? We have this. We're not done yet because we have here e to the minus 5s. We need to deal with this one as well. Well, so basically, this tells you here y of t is the inverse Laplace of e to the minus 5s over 2 times s plus 4 square plus 15 over 16. Okay, but this is simply what? Let's take 2 out, and this one we have here 4 over root 15. So it's going to be 2 over root 15. We have e to the minus 5s. From this, we have u5t, okay? And remember this here, let's call it age of t, okay? Age of t. So it's going to be age of, okay, t minus 5, so it's going to be the sine root 15 over 4, t minus 5, right? Times, okay, I forgot something here, I guess. No, it's okay. So this is, oh, wait. This is not ht, this is here, this is ht. So we work with this one, sorry. Times, here you replace t by t minus 5, e to the minus t minus 5 over 4, right? So because of here, this one, we have this term, and we shift by 5, right? The original function h, okay? Is that clear? Any question? Okay, we will stop here. Var mı soru arkadaşlar? Okay, I'll see you next week. Haftaya görüşürüz. Bye.
İyi günler hocam.
İyi günler.